Hi everyone and welcome back to another lecture of this series. So before we proceed, let us take a quick recap of the previous class to set the background of this class today. So right now we are discussing about the spark plasma sintering process, which is one of the most efficient processes for full density processing. And in the last class we have discussed about the basic fundamental mechanism of this technique, and there we have seen that spark plasma sintering is basically a process which uses the Joule setting. Here the heating takes place internally in the compact, unlike the conventional sintering processes in which an external heat source is used to heat the compact, right? So what we have discussed in the previous class is that there are basically three stages in the spark plasma sintering process. First, there is an electrical discharge between the particles when the electric field is applied, and this leads to an intense localized heating which leads to purification and cleaning of the particle surface for better bonding to take place between the particles. Okay, this also leads to a melting at the contact points because of the high localized temperatures, and that again is helpful in bonding the particles together for the densification to occur. Okay, and as I said, the heating here basically takes place by the Joule heating mechanism, where a pulse DC current flows from particle to particle through the necks and results in heating. Okay, and this kind of heating also results in enhanced diffusion and neck growth, right? So that ultimately leads to a faster densification in this process compared to the conventional sintering processes. And finally, when the pressure is applied after the heating has taken place, it will go through the plastic deformation and the densification will occur by the plastic flow. Okay, so this is what the basic mechanism of the spark plasma sintering process is. Now we'll continue on this and we'll see the further details of the SPS process. So when you talk about the SPS mechanism, it is basically the plasma heating and the plasma discharge which is set up in the gap between the particles, and that ultimately leads to this Joule heating which results in heating of the compact and densification. Okay, so here the electric field is applied through a DC pulse which is on-off type. So during this pulsing of the current, there are different phenomena which take place, and each of these phenomena have their own effects on the densification process and the densification mechanisms which occur during SPS. Okay, so this is a diagram over here which talks about this phenomena and their effect, and you can also see what practical advantage you get due to these effects. Okay, so when the DC pulse is applied, first you have this generation of the spark plasma as we have seen before, and this basically leads to surface activation, right? And then due to this sparking between the particles, intense heat is generated, and due to that there is evaporation, melting and purification. Okay, so due to the intense heat, the particles also melt at the contact points, and evaporation also takes place, and that in turn leads to the purification of the surface of the particles. Okay, so that's about the surface activation. And the practical advantage that you get out of this is the low temperature and short time of sintering, because the densification process is all about bonding between the particles, and when you have a clean surface, that bonding becomes easier, and therefore the sintering can be done at a lower temperature and the sintering time also can be lowered. Okay, then once the spark is generated, it will also exert some impact pressure on the particles, right? Because it is sparking. So you might have seen how sparking comes out with a force, right? So due to that, some kind of impact pressure will be provided when the spark is generated between the particles, and this basically leads to local stress and sputtering, and the effect of that is high speed diffusion and high speed material transfer for the neck growth that leads to densification. And the practical advantage of this is sintering of hard to sinter materials without any catalysis or any modification to the powder, and bonding of dissimilar materials can also be achieved due to this high rate of material transfer. Okay. Then this sparking leads to the Joule heating, as we have discussed, and that leads to local high temperature, and the effect of that is efficient heating and plastic deformation when the pressure is applied. So all these phenomena and their effects are actually interrelated, as you could see from these arrows. So Joule heating not only leads to efficient heating, but it also contributes to high speed diffusion. Similarly, the spark generation, it contributes to high speed diffusion as well as the surface activation process also, right? So there is a cumulative effect of all these phenomena, as you could see by these arrows, going to the different effects from a particular phenomena, right? And then there is action of the electric field, which leads to high speed ion migration, and the effect of that you can see again towards the high speed diffusion. And the practical advantages, as I said, is sintering of hard to sinter materials, right? Efficient generation of pulse voltage and current, and its effect you can see in terms of high density energy supply, dispersed movement of discharge point, and another effect is quick cooling of intergranular bonding. And this quick cooling is good for uniform sintering in a short period of time. And then there is thermal diffusion due to heat transfer from high temperature generating point, and this leads to again the same effect, the quick cooling of the intergranular bonding. And the practical advantage of that, you can sinter amorphous material, sintering of metastable phase, and low temperature sintering. So this kind of material where you need to preserve a particular microstructure or a particular phase has to be cooled down quickly, so that there is not enough time for any phase transformation or any changes that can lead to a change in the microstructure or the structure of the material, right? So therefore a quick cooling is always helpful for this kind of amorphous materials or materials having metastable phases. Now this is a diagram which again shows the different phenomena that occur during the SPS process from beginning to the end. So in the beginning, when the electrical field is applied, a potential difference is generated between the particles, as if they are acting as two electrodes, which can have flow of electrons in between them. Okay, and therefore this has to be done in vacuum, otherwise this kind of electron flow cannot happen. So this is a two particle model which is depicted over here to demonstrate the phenomena and the mechanisms of the SPS process. So this is in the initial stage of sintering, by that on-off pulse energization which occurs as the electric field is applied. And then this electric field leads to generation of the plasma between the particles, leading to ionization, and the effect of this is basically the melting of the particle contacts and vaporization. So this ultimately leads to the cleaning of the surface of the particle and also purification. So vaporization and melting actions of the particle surface are the next step once the spark plasma is generated. Okay. And the impact pressure which is created by the spark also leads to activation of the particle surface, which is again conducive for the bonding between the particles. So the phenomena here are generation of spark impact pressure and sputtering of vaporized and molten particles. And at the contact points, there is also rapid cooling, as we talked about before. And there is thermal diffusion also, due to the intense heating and the temperature gradient that you may have from the contact point towards the core of the particle. So this leads to material transport towards the neck. And here there is localized melting also because of the intense localized heating. And that is again good for the diffusion process at this neck. And when it is cooled down, this molten material will ultimately solidify, and as the pressure is applied, plastic deformation will happen and the densification will occur by plastic flow. Okay, so these are the different kind of phenomena which occur during the SPS process. And this is again a two-particle model showing the different diffusion paths which exist during the SPS process. These mechanisms of diffusion are not very different from what we have in case of solid-state sintering, except probably this vaporization and solidification which occur due to the intense localized heating as a result of the spark. Okay. But apart from that, you have similar mechanisms like volume diffusion, which occurs from the bulk of the particles towards the neck region, surface diffusion that occurs from the particle surface towards the neck, and of course grain boundary diffusion which occur along the grain boundary between the solid particles, right? Now let us see the process as such as to how it is carried out and what is there inside the SPS equipment. So here the powder is filled inside graphite dies, because graphite is conductive and through the die, therefore that electrical current can be conducted to the powder, and the powder is pressed by the graphite punches, right? The use of graphite here is basically to ensure that the current can be easily conducted to the powder particles. The heating rate is typically in the range of 10 to 100 degrees Celsius per minute, but it can be higher also depending on the material and the microstructure which is desired. And as I said, a DC pulse is used as the power supply, and the DC power supply is connected to the upper and lower punches, and through these graphite punches the current is conducted to the powder which is in the die. Here the current levels are very high, to the tunes of a few thousands of ampere, but the voltage is low, so it's a low voltage high current process, and DC pulse and pulse time is of the order of tens of milliseconds. Okay, and a pyrometer is used to measure the temperature. So here is the schematic of the basic setup that is used for SPS. So as I said, you have graphite die and punch sets which are used to pressurize the powder and also to carry the electrical current to the powder. And then you have this upper and lower ramp through which the powder is pressurized, and this upper and lower ramps are connected to the DC supply. And here you have the pyrometer to monitor the temperature. And this is how it would look like if you have a look at the SPS chamber when it is in operation. So this is a live photograph which was taken in our lab while the SPS was actually done. So if you look at the SPS process cycle, it is basically a 4-stage process. In stage 1, the SPS chamber is evacuated. So it's vacuum application stage. And once the required vacuum levels are reached, then in stage 2, the pressure is applied. Stage 3 is all about heating. Where the Joule's heating or resistance heating takes place, and the densification occurs under pressure. And finally, stage 4 is the cooling stage. This is also important because how fast or how slow the compact is cooled, depending on that, the microstructure can change. So SPS is a process which is quite often used for preserving a particular type of microstructure because of the rapid sintering which occurs here and the short sintering times. A particular type of microstructure can be easily preserved, which may not be possible in conventional sintering processes as the sintering cycle is quite long. So therefore the cooling rate or the cooling stage is also important in this case. And stage 4 is all about that. It can be also illustrated with the help of a diagram like this. Stage 1 vacuum application. Then once the vacuum is reached, the pressure is applied, that is stage 2. And in stage 3, the resistance heating takes place. And finally, once it is held at the sintering temperature for a particular period of time, it is cooled down. So that is stage 4. So pressure is increased continuously and the compact is then held at a particular pressure as the sintering temperature is reached. And as the heating takes place, the temperature increases continuously. All the way to the sintering temperature. And once the sintering is accomplished, it is cooled down. Right, so these are the 4 stages of the SPS sintering process. Now let us also have a look at the advantages of this process. Some of them we have already talked about before. You can achieve rapid sintering, and the sintering is also uniform because of the uniform heating that takes place. Less grain growth because of the short sintering time and faster cooling, and therefore nano or ultra fine grained materials can be easily processed by the SPS technique. Here binders are not necessary, unlike many of the conventional sintering processes where a binder is added to the compact to aid the packing of the powder particles. And compaction and sintering are combined in one step as the pressurization and heating occur simultaneously. And a high purity can be maintained here because of the purification of the particle surfaces, as we have talked about. When the spark is generated and there is local intense heating, it also leads to the purification of the particle surfaces by evaporation and melting. And all kinds of materials can be processed no matter what, whether it is a softer material or a stronger material. Even difficult to process materials can also be easily processed by this technique. And it also offers high energy efficiency. And as far as the operation of the sintering equipment is concerned, it is also easy to operate. Right? So because of all these advantages, in recent times SPS has become a quite attractive process to fabricate a large variety of materials for different applications. Okay, so we have been discussing about the different hot consolidation processes and their mechanisms in past few classes, including today's class. So now that we have learned about different techniques of full density processing or hot consolidation, it is time for us to have a quick recap and try and summarize these techniques. So the need for full density processing arises from the fact that it is difficult to remove the pores completely by conventional sintering, and therefore we need methods which can overcome such limitations of conventional sintering and give rise to a fully dense compact at the end of the sintering process, right? So full density processing basically is a method which applies the heat and the pressure simultaneously. So this is kind of combining the compaction and the sintering process in one step, unlike the conventional sintering process in which the powder is first compacted and then the green compact is separately sintered to achieve densification, right? But in this case, the powder can be directly sintered with the simultaneous application of heat and pressure to fully densify it. Okay, and the process which basically leads to this enhanced densification is the disruption of the surface films by the deformation that takes place at high temperature, right? So this will ensure that when the particles come in contact, a fresh surface is there for them to bond together. Okay, so the fresh surface will essentially give rise to a more effective mass transfer, and therefore the particles can bond together more effectively, giving rise to better densification. And if you look at the mechanism of this hot consolidation, where the heat and pressure are applied simultaneously, it basically resembles the creep phenomena, which is a high temperature deformation process that occurs at a constant stress. So at higher stress levels, the densification can take place simply by plastic flow. As the yield strength of the material is exceeded, it will start to deform, and the densification can occur through plastic flow along the necks which develop between the particles. Okay. And at lower stresses, the diffusional flow will combine with the applied stress, resulting in densification by the creep process. Okay, and therefore the equations for the mechanism of this hot consolidation process can be obtained by suitably modifying these creep equations, taking into account the porosity which is present in the compact. So once we understood these mechanisms, we went ahead to talk about the different hot consolidation methods. And we have covered these processes with regard to full density processing, hot pressing, which is basically uniaxial pressing in a die with the simultaneous application of heat and pressure. We also talked about hot isostatic pressing, in which the pressure can be applied from all direction uniformly, unlike the die pressing in which the pressure is applied along a particular direction, which is basically along the axis of the die. So this leads to a better densification when the pressure is applied uniformly through all directions. And then we talked about other two hot consolidation processes, and these were powder forging and powder extrusion. So this is basically deforming the powder inside dies to achieve the densification during this hot deformation. And then we talked about a process called spark plasma sintering, which is quite different from all other sintering processes that we discussed before it, because in this case the heating mechanism is completely different. Okay, so unlike the conventional sintering process or the hot pressing process, here in case of spark plasma sintering, the heating occurs internally by Joule heating. Okay, so here what is done is an electrical current is passed in the form of a DC pulse, and the heating is achieved with the heating effect of that particular current. Okay, so that is basically the Joule heating, which is the heating effect of electrical current. Okay, and this happens across the particle to particle contacts when a spark results due to the application of a very high current, and therefore the heating is quite intense and also uniform across the entire compact. Okay, so this results in enhanced diffusion kinetics, and as a result of that, a much rapid sintering compared to any other sintering process. Okay, and because of this enhanced densification, the process offers several advantages. For example, the efficient heating that you have in this technique will enable sintering of difficult to sinter materials. Okay, so there are certain materials which are difficult to sinter by other processes, but due to this enhanced diffusion kinetics and an efficient heating, the spark plasma sintering can easily sinter those materials as well. Okay, and the rapid sintering which occurs in this case will also allow us to preserve a particular microstructure which may be desired in the final product, or a particular phase which may be needed for achieving certain properties. That can also be preserved with the help of this particular technique called spark plasma sintering, because the sintering time in this case is much lower. It is in the range of few minutes to maybe couple of hours at max, compared to several hours or even days for the conventional sintering process, right? So due to this kind of rapid sintering kinetics, a microstructure can be easily preserved because there is no time for the microstructure to grow or change, as the sintering and the heating and the cooling processes occur rapidly. Similarly, if a particular phase has to be preserved, that can also be done, since again, as I said, there is no time for any phase transformation to take place, right? So these are the different advantages which can be achieved with the help of this spark plasma sintering, because of its efficient heating and the enhanced diffusion kinetics which result from the uniform heating that occurs through the generation of sparks between the particles. All right, so that's all I have. But today I am not going to say what I normally say at the end of each lecture. I am not going to say that with this we come to the end of this lecture and I am going to see you soon again. Because with this lecture, we have in fact come to the end of this particular course. Okay. But this course can never be completed before I acknowledge the tremendous amount of support that I have received from different corners throughout the entire duration of the course. So first and foremost, I would like to thank the NPTEL and the SIAM platforms and Government of India for supporting these great initiatives. Having said that, I would like to thank the administration of IIT Madras for putting up and giving access to all the infrastructural facilities for creating this content. In fact, IIT Madras has put up a great NPTEL team who have been working relentlessly behind the screen to create all the video content, including this particular course. And I have received every support from this team throughout the entire duration of this course. And I am really grateful to the entire team, but I would particularly like to mention my camera cum editing crew, Mr. Vignesh and Mr. Ravichandran, and my graphic designer, Mr. Rajesh Kumar. Without their help and support, it would have been never possible to create this content. And last but not the least, I would like to thank all of you who have connected to this course through this particular platform. It goes without saying that this course would be never complete without your participation. So thank you for connecting with us. It has been a pleasure for me to connect to all of you. I hope you have found the content useful, and I do look forward to receiving your feedback. So with that note, it's time for me to sign off. Thank you one and all.